Hello friends, now we will see one university question on calculation of deflection by Morse moment area method. This is for Annamalai University for the year May 2018. It is a cantilever beam of length 2.5 meters. It is uniformly loaded with an intensity of kilonewton per meter, length of 1.3. The beam length is 2.5 meter and the loading is done for a length of 1.5 meters from the fixed end. We have to determine the slope and deflection at the free end of the cantilever using moment area method. The given data are I is equal to 9,500 centimeter per 4, E is equal to 200 Newton per meter square. This is for Annamalai University for the year May 2018. Now, we will convert these units for the sake of the length is given in meters. The length is given in meters. So, we will convert this moment of inertia into meter power 4. It becomes 9,500 centimeter power 4 becomes 9,500 into 10 power minus 8 meter power 4. Young's modulus is given in Newton per meter square, whereas the loading is given in kilonewton. So we will convert this into kilonewton per meter square. This is equal to 2.1 into 10 power 8 kilonewton per meter square. Now, what is Morse theorem number 1? If you take 2 points, say A and B, and if theta A and theta B are the slopes between the 2 points, then theta B minus theta A is equal to area of the bending moment diagram between point B and A. This is Morse moment area theorem number 1. A is fixed end. Therefore, slope at A is 0. That means theta A is equal to 0. Theta B, it is free end. It is a slope. Slope exists at theta B. And let us apply the theorem for the points B and A. Theta B minus theta A. Theta A is equal to 0. That means theta B minus theta A is equal to theta B itself. That is equal to 1 by A times the area of the bending moment diagram between the points B and A. Here, between B and C, there is no load. So there is no bending moment diagram between B and C. Between C and A, load is there, and bending moment diagram we have to draw. And if you take C as the origin at any distance x, bending moment is equal to 10 times x, because it is uniformly distributed load 10 times x. Its resultant is acting at a distance of x by 2. Therefore, 10x squared by 2 is the intensity of bending moment ordinate at a distance x measured from C. Let us consider a strip of width of dx. Now, area of this elementary strip is equal to 10x squared by 2 into dx. At any distance x, bending moment is equal to 10 into x by 2, 10x squared by 2. Width of the elementary strip is dx. Area of the elementary strip is 10x squared by 2 into dx. C is taken as the origin. We have to do the integration for getting the total area of the bending moment diagram between C to A. That means the limits are 0 to 1.5. And that is what has been written here. The limits are 0 to 1.5. 1 by A times 10x squared by 2 is the bending moment ordinate into dx. This is the area. So EI goes to denominator. This is E kilonewton meter square. This is I in meter power 4. 10 by 2 will become 5x square integral dx will become s power 3 by 3. So 5 by 3 into s power 3. Upward limit is 1.5. S cubed will become 1.5 cubed. Lower limit is 0. So upon simplification, we are getting this radians. Slope is obtained in radians. If you want it in degrees, multiply this by 180 divided by 5. This much into pi divided by 3.14 will give you the slope in degrees. So theta B is equal to this much. This is the slope at the free end. Now we have to get the deflection at the free end. Now we will apply Morse theorem number. A is one point. From this you draw one tangent. At A the slope is 0. That means if you draw the tangent it will be horizontal. At B you drop the vertical intercept. This is the vertical intercept B. Dropped on the tangent drawn from A. From A you are drawing a tangent. From B you are dropping the vertical intercept. That is denoted by YB. And this YB happens to be equal to delta B. That is deflection at B. Please note, deflection is not given by Morse theorem directly. It is given indirectly. It is given the Morse theorem gives the vertical intercept on a particular tangent. It is drawn from point A. Vertical intercept is dropped from point B. The vertical intercept YB happens to be equal to delta B. And if you calculate YB, then you have to calculate the moment of the area of the bending moment diagram between B and A. And moment means a bending moment diagram into the distance. Distance should be measured with respect to the point where you want the vertical intercept. Here you want the vertical intercept at point B. Therefore, the bending moment diagram, you have to take the moment, the bending moment diagram about the point B. Now, at any distance from C, the bending moment ordinate is equal to 10x square by 2. 10 into x is the total load. X by 2 is the resultant. 10x square by 2, bending moment ordinate. Consider an elementary strip dx. So area of the bending moment diagram is 10x square by 2 into dx into integral. Limits are C is the origin. C to A means 0 to 1.5. And we have to take, this is the bending moment diagram. 0 to 1.5 into area of the bending moment diagram. What about the moment of the bending moment diagram? You have to multiply this by the distance. The distance should be taken with respect to the point where you are measuring the vertical intercept. Here you need delta B, which is equal to YB. YB is the vertical intercept. Therefore, you take the distance with respect to the point B. From B to C, it is 1 meter. For the general expression, the distance is x. Therefore, this ordinate is located at a distance of s plus 1. This is the area into distance. This gives the moment. Area is 10x square. Width of the elementary strip dx. Area. Distance is x plus 1. C is the origin. 1 meter. B is the point from where we are measuring the distance. So this elementary strip is located at a distance of s plus 1 meter from B. This is the moment. I goes to the denominator. E in kilonewton per meter square, I in meter power 4. There are two terms. It becomes two integrals. So first term 10 by 2 will become 5. X square integral will become x cubed by 3. And the second term is 1. Therefore, it is 5x square. It is 5x cubed by 3. And the first term is multiplied by 1. Therefore, it is 5 into s cubed. And you have to apply the limits 0 to 1.5. So this is s power 4. This is, first term will have s power s cubed, 10x square multiplied by s plus 1. First term will be having x cubed. Second term is having x square. Therefore, it is s cubed by 3. 1.5 cubed by 3. This is s cubed integral. It is 1.54 divided by 4. 10 by 2 is 5. There are two terms of integral. Upon simplification, this becomes so many meters. That one you multiply by 1000, you will get the deflection in millimeter. This is the solution for the deflection calculation by moment area method. And please visit my website https://rgnsite.wordpress.com. It contains nearly 500 university questions and answers on various structural engineering subjects, RCC design, steel design, structural engineering for DCE examination, strength of materials and structural analysis part 1, strength of structural analysis part 2, such as moment distribution method, slope deflection method, arches, cables, suspension bridges, matrix methods, force method, flexibility method, deflection calculations, steel design, RCC design. About 500 university questions and answers are available and the download is free. Please visit my website https://rgnsite.wordpress.com. Also visit my YouTube channel RGN Class. My YouTube channel ID is RGN Class. Small letters RGN Class. Thank you.